UT Austin, and he's currently with Amazon Far Labs. And until recently, he was a postdoctoral researcher at UC Berkeley with Professor Peter Avil. His research focused on advancing humanoid robots' intelligence and local manipulation capabilities by incorporating priors, inductive biases, and multisensory feedback. He earned his PhD from ETH Zurich under the supervision of Professor Raffaello D'Andrea, where he developed vision-based, data-driven tactile sensors and explored their applications in robot control and dexterous manipulation. Carlo is a recipient of the Best Demo Paper Award at RSS 2025, the 2022 ETH Medal, the Best Paper Award at RoboSoft 2022, and the 2017 ETL Award. He was also selected as a Rising Star at RoboSoft 25 and RSS Pioneer 2022. Well, with that, it is great again to have you, Carlo. Please take it away.
Hi, everyone. Yeah, thanks for the kind introduction, also for having me. Very happy to give the talk today. So I'm not sure if there is a possibility for you to ask questions, but if there is, feel free to ask those at any time during the talk. I've accounted for that time. The title of the talk is very broad, and that's on purpose because I really want to give you an overview of the general ingredients we are seeing bringing progress to humanoid robot learning, and especially want to go through what makes it different from all the rest of robot learning. And this concept video from Tesla gives away the main objectives of research in humanoid intelligence. That is to bring robots as assistants in our lives, to improve quality of life of millions of people, taking care of tedious chores that we would rather avoid, especially at a later age and for the elderly, such as unloading a dishwasher, picking things up from the ground, or carrying heavy loads.
Just a moment, actually, Carlos. My first question, an important one. We don't see your slides right now.
Oh. Should we try again?
That's the same. Weird. I can see them.
Yeah, it's the same to people on Zoom.
I can see them.
Yeah, me too.
All right, keep going then. Forget about it. We're just not figured.
Okay, should I go? I can also wait.
Yeah. Keep going.
Okay. So summing it all together, we basically want robots to assist with not just one task, but any task that humans want assistance with. And this vision has been kind of the dream of many researchers in robotics and AI, even outside humanoid research. But we all know we are not quite there yet. We unfortunately don't have such a robot in our home. So what we're trying to answer today is, what are we missing to have robots reach this degree of intelligence? How do we get a robot to assist humans in every task that we would like to automate? Well, on the hardware side, the background story is that the robotics industry has taken an incredibly sharp turn in the last couple of years by starting the development of all these new humanoid robots, very much replicating the human morphology and the human hands. Now, I like to call this the humanoid summer in contrast to the famous AI winters, but the reality is that there are some very solid reasons behind this current wave. So why humanoids? Why not any other robot? Well, the appeal of humanoids can be summarized in this sentence: solve all human tasks, as we already mentioned, but do it in human-centric environments and using tools that were made for humans. And the impressive hardware advancements that we've seen recently put us much closer to this objective, with legs and hands that are going to be much more adaptable to human-centric environments compared to wheeled robots with parallel jaw grippers. Now, because of their morphology, humanoids can particularly leverage minimal cross-embodiment gap with humans, which is particularly important if we want to learn to do things that are done by humans. For example, humans can act as teachers. And they also provide a strong inductive bias, meaning that, again, because of their embodiment, they will tend to do things the way we want them to, even if they explore on their own. However, humanoids are complex machines. They can be very costly and somewhat are not very safe to operate because of their weight and their power. And from a learning perspective, humanoids are also complex, high-dimensional systems, and I will show you how this particularly tends to make the learning problem very, very challenging compared to other robots. So our main theme of today's talk is going to be, how do we get humanoid robots to learn virtually any task? And ideally, how can they do it in a safe, scalable, and tractable way? So outline of this talk, I'm going to quickly talk about benchmarking humanoid intelligence and exemplify some of the challenges or the major challenges when dealing with these robots. Then we'll start to look at how we go around these challenges by making progress on several fronts of robot learning, tools, data, algorithms, and architectures. And finally, we'll look into what is missing from today's picture. So where are we at? Well, say we want to devise a set of tasks that encompass what we eventually want to achieve with humanoid robots. But for sure, there is locomotion, both on flat ground and on diverse terrains. But more importantly, what we really care about is interact and make changes to the world, which humanoids can potentially do through loco manipulation, which means doing both locomotion and manipulation at the same time. And this goes from everyday tasks, such as opening a door or operating in the kitchen, to tasks that really push the limits of what we can do with a human-sized robot, which really require all body coordination, for example, to carry heavy objects. So some time ago, we put all of these tasks together in a simulation benchmark, HumanoidBench, which was at the time the first of its kind simulation benchmark of humanoid intelligence. Now you could ask yourself, why did we need a new benchmark for this specific domain? Why not using one of the other robot learning benchmarks out there? Well, the issue with other benchmarks, say DeepMind Control Suite for locomotion or RLBench, RoboSuite for manipulation, is that they deal with one skill at a time, either locomotion or manipulation. On the contrary, we show that by featuring loco manipulation tasks, HumanoidBench is setting a very high bar with state-of-the-art reinforcement learning algorithms struggling at most complex tasks. And in fact, what makes such a difference is that the robot policies fail to acquire many skills at once, like balancing, walking, manipulating objects, and so on. And the only tasks that we could solve at the time were very similar to those of other benchmarks at addressing just one skill at the time, in this case, just locomotion. But there is something else that we noticed when we were developing HumanoidBench, which gives even a deeper explanation of what was leading this state-of-the-art algorithms to fail. And I can already disclose the main insight here, which is the fact that the learning algorithms struggle to deal with large action spaces. So what is an action space? Well, you can think of it as the space defined by the number of actuators or the degrees of freedom of a robot. And if you look at our humanoid, it has 61 action dimensions. But if we don't consider the hands, this quickly drops down to just 19. So here is a small case study. We performed experiments where we use a state-of-the-art reinforcement learning algorithm to learn to walk in HumanoidBench and investigated the difference between doing it with and without the hands attached to the arms of the robot. So what you immediately notice here is that removing the highly dexterous hands from the system improves learning performance significantly, and here, of course, I'm showing the cumulative reward over time. So as I mentioned, this confirms that the main bottleneck with these algorithms is their struggle with the high-dimensional action space of our simulation environment. And that's a big difference with what we're used to before, because in reinforcement learning for years or decades, we have studied and solved problems that dealt with large dimensional observation spaces, like learning from pixels. But the actuation space was always in the order of a few to maybe 10 or 20 action dimensions. So here, potentially, we have hundreds, and as we move more and more high degree of freedom machines, this becomes more of a problem as we want to deal with the actual complexity of the real world. So how do we make progress from here? Well, let's first look at how we can scale learning tools to reduce experimentation time, which can be a big hurdle when dealing with high-dimensional systems. And let's start from probably the most common paradigm to deal with humanoid robot learning and with like robots in general, which is a sim-to-real reinforcement learning. So how does that work? Well, you model your robot and ideally the environment in simulation. Now, there are going to be things that are not known, and in that case, you do domain randomization, meaning that you randomize the physical parameters or the scene appearance to ideally cover the distribution that you expect in the real world and make your policy robust to it. Then you try things on the real robot without any adaptation, and that's what you usually call zero-shot sim-to-real learning. The issue is that oftentimes things look great in sim, but in the real world, the robot behavior can be very different, indicating that there is a gap between sim and real. So how does it really work then? Well, the thing is that it's not just sim to real, but often is sim to real, and so on in a trial and error loop in practice. And between different iterations of this loop, there are a few things that we can tweak. And these are the robots in the environment, the reward signal, and finally the simulator. And in the next few slides, I'll only be talking about the simulator. So again, what we saw is that basically it is never zero shot sim to real because you build your simulation environment, you transfer a policy to the real robot. Depending on the behavior, you often come back to the simulator, either because you identified better a certain physical parameter or because you want to tune the reward to make sure that you stay away from messing things up in the real world, or because you want to randomize things differently and so on. So it's a loop. And if you want to keep things tractable, it's extremely important for this loop to be fast and interactive. And I really want to emphasize this because training in simulation can still be very slow. Probably many of you have seen this example by OpenAI where they could solve a Rubik's Cube already more than 5 years ago. And they were also training entirely in simulation. And they made plenty of simplifications to their simulation environment as well in the task definition, but it still took days to train a policy that could successfully transfer to the real world. Now, because sure, simulation is safer and more convenient than training in real, but if it is as fast or slightly faster than real time, then it is still quite slow. So I'm resurfacing this plot from the HumanoidBench slide before, where we saw that learning with high-dimensional humanoids requires many more simulation steps. But maybe 10 million steps, for example, here, are not as many if we can do them very, very fast, leveraging advanced compute such as that provided by GPUs. And that is exactly the idea behind IsaacGym by NVIDIA, which basically used a GPU implementation of a physics engine, PhysX. And this way, one could place both the simulation and the policy directly on GPU, which can have thousands of cores to massively accelerate reinforcement learning training. So basically, this was still using existing algorithms simply by scaling up the number of parallel environments where the agent collects its own experience. But now if you look at the x-axis here, we're talking about seconds, which is incredible when the same policies took days to train before. So the issue, though, is that this platform was closed source. And for physics simulation, full visibility is actually very important, and I'll tell you more about it in a few slides. So I'm going to first introduce another software library that goes in the same direction of IsaacGym, but it is fully open source instead, and it is MuJoCo Playground. This was a collaboration between our group at Berkeley and the MuJoCo team at DeepMind, and we released it at the beginning of this year. And it wants to further accelerate GPU parallelized robot learning as well as sim-to-real transfer. It spans both locomotion and manipulation environments, and it has shown to be successful on a variety of different robots and tasks. Now, differently from IsaacGym, it's entirely written in JAX, meaning that the environment code, the algorithms, and the physics engine, which is MuJoCo MJX, are all written in JAX. And that resulted in native scales to multi-GPU settings, meaning that you can easily make things faster with more compute. And it leverages the MuJoCo simulator ecosystems, which means cross-platform compatibility, and one of my favorite features, which is this interactive viewer that really works great to find failure modes in the reinforcement learning policies. So back to why open source is particularly important in this setting. Playground is fully open source, and this means that you can freely introspect into the simulator and adapt it depending on your training scenario. Now, an example of this is that if you want to include rendering in your pipeline, having an open source API makes it very easy to do that. And for example, in MuJoCo Playground, we show that you can easily plug in an open source GPU renderer, Madrona in this case, and seamlessly augment your training loop with randomization of visual appearances. And the open source community can keep doing things like this every day, right? Which is really pushing the maturity of and the completeness of this code base. So we trained many locomotion policies, starting with quadruped robots on Playground. These are all classical joystick policies, but also more advanced tasks such as fall recovery or handstands. All these policies were trained on GPU in about 5 minutes each. And the same goes for humanoids. You can see here several bipeds and humanoids trained again with MuJoCo Playground and a similar recipe as in the previous slide. This time it was slightly longer training time. And it's not only about locomotion. Playground also works well for many manipulation tasks, as you can see here, both for dexterous hands, but also for compliant manipulation. Now, while the previous policies were all state-based, we also show some simple tasks that are instead pixel-based using the Madrona renderer that I was mentioning before. And here, the fact that we are introducing visual scene randomization makes the policy also very robust to any kind of distractors. And we also shown that the physics engine is actually really good. Here you see a get-up maneuver in simulation. And surprisingly, it also works very well on the real system. And by the way, this is not cherry-picked. It's actually a very consistent policy, and we demonstrated it for a full day in front of a big crowd at the last RSS conference. I like to be upfront on the limitations, especially if we talk about practical tools, and the MuJoCo Playground is also still a very recent project. So first, it takes some time at the start of training to JIT compile. And another JAX limitation is that the computation scales with the number of potential contacts rather than the number of actual contacts, which is not that desirable for complex environments. On the bright side, MJ Warp was announced at this year's GTC, and it is already supported in MuJoCo Playground, changing just a few lines of code, and it provides up to 100 times speed up on some contact-rich manipulation tasks. Or you could also look at the follow-up by Kevin, MJLab, very recent, which is basically following the same design principle as NVIDIA Isaac Lab, but basically still allows you to use MJ Work and MuJoCo as backends with some of the advantages that I just mentioned before. Any questions so far before I move to the next part? Great. So we looked at in improving tools, but how about improving the algorithm?
Sorry.
Sorry.
Do you mind if I ask a quick question?
Go ahead.
Because I guess because you seem to know a lot about the simulators and some of the details. I've also been interested to know more about like there's things you can accelerate, but some things that are still challenging. So maybe you can comment on like how are the contacts computed, and are those still pretty fast and accurate? Because some of our group wants to build on this and use it for like manipulation problems, assembly problems, things like that.
Yes.
Have you got some tasks in that area or some thoughts?
Yes. So the thing I like the most about MuJoCo, people like to talk about contacts are accurate in MuJoCo versus like Gym or something like that. I think the reality, I think that the big point about MuJoCo is that the contact model is extremely general from an optimization perspective. You can basically tweak any little parameter. Okay, like I can think like I see you can see this task here, this orca hand here. This hand here has a lot of softness in the material. This is basically silicone rubber. So there are a lot of issues. So I remember like I deployed the first policy and the cube was getting stuck. And I think then the reason was that I wasn't modeling softness properly. And in MuJoCo, contacts can also be softened. And you can do these kind of things, and the policy gets much better. But then you see you still get stuck when rotating, and then you can now model torsional friction because you have a lot of parameters to do so, and now the policy improves even more. So I think this kind of sometimes we always think about getting things accurate, but I think sometimes it's also good to have things as flexible as possible. So I would say like in MuJoCo, we've seen like you could model basically almost everything up to kind of almost rigid body. Then of course there are issues with at the interface with very deformable bodies. I think that's like still a big open questions, and we haven't really like figured out yet without spending too much compute on how to bring these things at the same level of performance compared to rigid body simulation. I'm not sure if that answered the question. It was more about the tasks.
That helps. Thank you.
Okay, so I want to look at tools next. If I look at tools first, I want to look at algorithms next. And of course, algorithms you can use within these tools. Now, the algorithm that has been used the most for sim-to-real RL in robotics, I'm sure you know both in MuJoCo Playground or Isaac Gym, this is PPO, proximal policy optimization. And curiously, it is the same algorithm that was used to fine-tune the ChatGPT model response based on users' feedback on an initial release. Now, the nice thing about PPO is that it is extremely lightweight and very fast. It is based on what we usually call a non-policy update. which means that the robot collects a lot of data in the environment, then he uses this data to update the policy, then throws away this data and starts again. And you notice from the sequence that though it is effective, PPO is not really sample efficient, meaning that it doesn't make good use of all the data that it collects, because every time we update the policy, we need to recollect data from scratch in the environment. And a consequence of this is that PPO is hard to fine-tune in the real world, because in the real world, it is much more important to be efficient. But that said, it's still pretty good for zero-shot sim to real. But can we do even better? Well, it turns out that we can actually use off-policy reinforcement learning for the same purpose. A difference here is that the data that the agent collects goes all in the replay buffer. And the off-policy update then looks like this. We first collect a bit of data and store it in this replay buffer. Then we sample a batch of data from this replay buffer, and note that this doesn't need to be data that was collected all most recently, but it's actually better if this data is diverse. Then we update our policy and repeat. Now, the result of this process is very simple and a simple, efficient algorithm. But a big question that was unanswered for years was, can it scale well to a large number of parallel simulation environments, similar to how PPO does that? But also, does sample efficiency really matter that much when learning in simulation? Well, if we look at research in off-policy reinforcement learning over the years, people have done incredible progress in sample efficiency. These are the results from a paper on TD and MPBC. I just took it as a sample, which showed how they can do much better on HumanoidBench in terms of sample efficiency compared to, for example, TD and PC2. But that comes with a price in all-time efficiency. Now, of course, if sample efficiency gains are huge, that's still great. But for training in simulation, what we really care about the most is wall time. So samples are cheap in simulation, but what is expensive is the time that we spend using our training compute. But still, it would be nice to have an algorithm that is both fast and sample efficient, so that we could use it to train our policies in simulation, but also if we want to fine-tune them in the real world. So we wanted to find an algorithm that is both fast and sample efficient, and this was the motivation behind FastTD3. It is based on TD3, which is an off-policy reinforcement learning algorithm developed back in 2018, and uses, as many other algorithms, an actor, which is basically the policy used for decision making, and a critic, which is basically rating how well the policy is performing with the decisions it takes at each step. Now, the interesting thing is that FastTD3 just reuses concepts that were already there in the reinforcement learning literature, but were never put together with the purpose of making sim-to-real reinforcement learning both fast and sample efficient. So let's look at the improvements. The first thing that FastTD3 does, compared to the original TD3 implementation, is to use a much larger number of parallel environments, similar to PPO. Now, the second improvement is using large batches during training. And you remember the off-policy update? We sampled some data from the replay buffer to improve our policy. And it turns out that if this data is diverse enough, you'll get a better policy improvement. So it makes sense to have a larger batch to cover more diversity. Also, if the replay buffer is large and we use just small batches, well, some of the data will never be seen by the algorithm. So the use of large batches is again beneficial to avoid that. Other improvements are distributional RL. I talked about the critic, which is basically rating how well the policy is doing. Instead of outputting a continuous value to rate the policy, we basically discretize the value space and output a distribution over these discrete values. And since this is a categorical distribution, we train with cross-entropy loss instead of a standard mean square error. And finally, we use larger networks and the technique known as clipped Q learning that basically stabilizes learning of the critical network. Again, all of this was out there in the reinforcement learning literature, but putting all of it together makes things work much better for sim-to-real learning. Now, the nice thing is that FastTD3 actually works very well for both CPU and GPU simulators by accordingly scaling the number of training environments. It achieves state-of-the-art results on HumanoidBench, and it does it much faster than all the other competitive algorithms. And as mentioned, it works great for GPU simulations too, where parallelization can be exploited even more. So this is what I was talking about with FastTD3 outperforming all other algorithms on HumanoidBench as well as in Playground and Isaac Lab. And importantly, here on the x-axis, we have world time in seconds, but you also see in the paper in the sample efficiency curves where facility tree is still much better than on-policy algorithms like PPO. So of course, here we also have real-world results confirming that we can get really good policies by training with this new algorithm. Any questions so far?
Yeah, I have a question.
Yes.
So great work. In the paper, I think you used an MLP, right, for FastTD3.
Mm-hmm.
Have you done experiments since then with like transformer or bigger networks?
Yeah, so that's a good question. This is something I really care about because it's very related to the next topic I'm going to introduce, the body transformer. Um, Training transformers from scratch or reinforcement learning has been very challenging, like very large networks. I mean, there has been a lot about scaling MLPs for off-policy learning, which is something with ION with Facility. But not much with transformers. Like there has been something, but I mean lately, like a core, there was this paper that got very popular. The locoformer from Skilled, where apparently it seems like to really train a big transformer, you need a lot of compute. Like I think they were using something like 160 GPUs for training and huge batch sizes at the level of LLMs. So I think that is very promising. In our experiments, if you just try to train a transformer the same way you would train a classical large NLP, that wouldn't work that well without any representation learning. With representation learning, I think you can probably match the performance.
Okay, thank you.
So we talked about moving towards better algorithms with FastTD3. Now, I mean, this question just introduced it. I want to briefly talk about the learning architecture, which is basically the neural network that we use to model the policy. Now, the reason why I'm interested in this is that, as I was saying before, like we ideally want to fine-tune policies in domain, but we cannot expect a robot to always do very well zero shot, right? Because that's not human to do either. But imagine we fine-tune, let's say, a large transformer policy that is controlling a humanoid to do fine manipulation in the real world. But those fine-tuning updates should ideally affect the behavior of the upper body of the robot, but should not let the robot forget how to balance itself, as this is not really contributing to the fine manipulation. So all such things are made challenging by the use of monolithic black box architectures, and this is a very broad topic we could talk about for hours, but I want to show you a first attempt to move towards more interpretable separation or controlled signals across policy architectures. So in particular, if you look at the transformer architecture, which has already been used with success also in robotics, this neural network architecture was originally conceived in machine learning for language models because it can capture global relations in observation sequences such as language, which can be largely unstructured. But this is very different than what happens in humans and animals, where the nervous system is routed following notions of locality, which is what actually allows us to have reflexes and fast reactions at the level of the spinal cord. So we could ask ourselves, is locality just an evolutionary artifact with no tangible contribution to learning, or can it play a role in the way robots learn? So the question is, how can we effectively encode the body information into the transformer architecture, which is, again, pretty popular and successful also in robotics, but leverage it even more in this setting? So the idea behind this novel architecture, the body transformer, is essentially to bias the vanilla transformer to take into account the structure of the robot body. In practice, we treat the robot body as a graph and separate sensors and actuators by assigning them to different nodes of this graph. Then we manipulate the attention mechanism to make sure that at every layer of the encoder, a node can only attend to itself and its direct neighbors. Now, by doing this for more subsequent layers, provided that we have enough layers, we don't lose any representation power, but we just guide learning in a way that the first layers only look at local information, while the deeper layers have a more global context. So in the way we construct these attention masks is very simple. We represent the body as a graph of nodes, where each node is part of the body. and compute the adjacency matrix. Then we add ones to the diagonal to make sure that each node can also attend to itself. Now, what I want you to note on this slide is that embodiment masks are typically very sparse because a robot limb is only connected to a few other limbs. So in practice, this attention computation can be done in a much more efficient way, which leads to large benefits in terms of computational efficiency. And by exploiting sparsity, if we look at the time it takes for a forward pass, well, the body transformer reduces that considerably by more than 2 times. And the advantages get better and better as we grow the number of nodes in the graph. So again, it's very beneficial for high-dimensional robots such as humanoids. But now the interesting thing is that it is not only about computational efficiency. And in fact, we compared the body transformer with classical MLPs and transformer baselines and noticed performance improvement across a variety of scenarios. So we note here is that with a large-scale multitask dataset for imitation learning, it achieves higher returns, but also scales better than the vanilla transformer when we increase the size of the model. Basically, it doesn't overfit, and this shows potential to absorb large amounts of data. Our body transformer baseline also achieves state-of-the-art, and this benchmark where previous methods were extremely tailored to this task, using recurrent neural networks to infer the intent of a specific trajectory, while we use simple plain behavioral cloning with just a different architecture. We also see advantages in a low data regime, and on the right here, we show that the body transformer is consistently better than the vanilla transformer, and is also competitive with the MLP, which is usually thought to be a better choice when using a very small amount of data. I unfortunately don't have time to show that today, but the body transformer also works really well in a reinforcement learning setting, where you need to get the details right, but we show that we can use it in a sim-to-real setting to transfer policies to real-world systems as well. So now we are missing the last component of the learning process, and some would say it's the most important, and that's data.
Do you mind if we ask some questions about that?
Yeah, of course, take it.
I guess I was wondering about, some comparisons, because there's some work in this area from like metamorph and anymorph. So then how do those methods compare to the body transformer you just explained?
So I think there is a different focus here. Like I think you're referring to methods that, for example, were used for cross-embodiment learning. There is a bunch of those, especially like years back. I think here the message of the work was a bit different. It was, I mean, of course, if you want to use something for cross-embodiment learning, it's great to have some structure information in the architecture because it helps you adapt when you see even a newer embodiment. In the body transformer, it said the message is even for a single task, for a single robot, inductive bias matter because we don't have an infinite amount of data, at least yet. So that's kind of the main difference. In practice, the difference is that the fact that we don't have to focus on cross embodiment allows us to do things like having specific tokenizers, so the joins are specific detokenizers to output the actions. So that's I think like the main difference from an architectural perspective. I think like before body transformer, I think most works were using just graph neural networks, and just transformers are a better much more well-behaved architecture to train with, which makes like a big difference for this kind of problems as well.
All right, makes sense. I guess just one other quick question. Is there any way to like exploit the like sparsity of that matrix now? Because like you don't need to compute the entire matrix right in every point. So is that also done in your work?
Yeah, that's what we show here. This is the one in blue, actually a re-implementation of the PyTorch vanilla attention. Of course, we're not comparing with fast attention. We're just comparing, apple to apples, and just as you said, like basically make like the computation in a way you don't use like the nodes that you don't need. Yeah, you can do it much faster because basically you can convert a matrix multiplication and dot product, and it makes it much easier.
Okay, thank you.
So data. Here I want to take a step farther on everything. Start thinking about how we make humanoids solve complex long horizon tasks that require doing both locomotion, manipulation, and in general interaction with the environment. Well, the issue is that in addition to a high dimensionality for a problem like this in the pictures, it's very hard to even design a reward function. as there are multiple stages and many different components, and also there is usually an expectation for humanoids to kind of follow natural motions, similar to that of humans. And in fact, a way to get this sort of natural motions comes from the character animation community in computer graphics. It relates to tracking human motion with a similarly shaped character, for example, a humanoid in this case. The procedure to repurpose human position and velocity trajectories to the human joint space is called kinematic retargeting. And this is at the base of what we call motion tracking for humanoids, where we start with a human reference motion, so we retarget it to a robot reference motion. The kinematic retargeting generally only takes into account positions and velocities, so a way to add dynamics information is to train a tracking controller in simulation that, if properly domain randomized, will be able to transfer to the real world. So this procedure is basically what leads to all the dancing demos, very impressive, that you might have seen on social media lately. But why? Why are you still seeing just walking, running, or dancing? Well, the issue is basically that we are missing a kinematic retargeting procedure that considers interaction with the object and the environment, while still providing high-quality kinematically feasible trajectories that is possible to track even in the most challenging cases. Now, one of the most popular approaches to kinematic retargeting is key point matching, which minimizes the Euclidean distance between some key points selected both on the human and the robot. However, the robot can have completely different proportions than the human demonstrator, and simply scaling the key points, for example, using the height of the robot, often results in penetration when dealing with objects. Now, in contrast, we leverage a concept called interaction mesh to preserve spatial relationships between the body parts and with body parts and with objects and environments. Basically, we sample key points not only on the human and the robot, but also on the object. And then we construct this interaction mesh that allows us to explicitly keep track of the relations within all the different points. Then the way OmniRetarget works is basically by framing this as an optimization problem that minimizes the difference in deformation between the human and the robot, subject to a series of hard kinematic constraints. And the resulting motion is smooth and consistent with the object that remains naturally in contact with the robot during the entire trajectory. On the left is the interaction mesh of a human that has provided the motion, and on the right is the one of the humanoid with the object. Now, the interesting thing of having a well-framed optimization problem is that now we can augment this data by simply changing the initial conditions of the optimization problem. And for example, we can vary the initial location of the robot with respect to the object, or the size of the object. And the optimizer will make sure to respect constraints while finding the appropriate modifications to the motion. And of course, you can do it for multiple robots and get like a very diverse data set. And finally, we can use these motions to deploy them to the real world by learning a tracking policy using reinforcement learning, as you see here, with very simple reward terms that basically deal just with tracking the trajectory and with energy minimization. I want to show you some results. Here is the robot picking up boxes of different sizes and then climbing onto platforms of different heights. This is in simulation, and then you see in the real world the robot keeps figuring out different strategies accordingly. And you can finally combine everything here with the robot that first carries a heavy chair to a platform. It uses it as a stepstone to climb up, and then starts leaping off. And it does so by performing a parkour-style roll to absorb the landing impact. You can see the slow-mo here. Now, kind of counterintuitive fact here is that all these policies are effectively blind, showcasing how accurate the original trajectories must be for the robot to only rely on proprioception to accurately follow the trajectories, of course, in similar scenes as those seen during training. And this pipeline is really mature, can push the limits of what the hardware can achieve. Here you see OmniRetarget enabling a highly dynamic wall flip motion, where we explicitly model the interaction with the wall during retargeting. And here the robot reaches maximum linear velocity of 3.5 meters per second and this quite impressive peak angular velocity of 15 radians per second. You'll see it one more time at full speed. Any question on this part to conclude the core part of the talk, at least?
Yeah, I have a small question. So you're saying the policy are blind. So does that mean that like in the real world, for your testing purposes, you had to, I don't know, add some type of sensors on the objects?
Oh, no, the objects are not tracked either. It's completely blind. Basically, what happens is that in the real world, we just make sure that the objects and the the chair, for example, or the platforms are basically in the same configuration or similar configuration to those encountered in simulation. We do have some augmentation with that as we generate as well through the optimization problem. But there is also proprioception, right? That gives you some kind of implicit feedback, implicit contact feedback. Let's say, usually the input to the policies are current state, proprioception, and the last action. So imagine there is some contact, and then let's say you have your robot pushing towards this contact in the previous action. Then if at the next time step the state is different than when the robot would expect without contact, then it figures out that there was actually something in the middle. So that's kind of almost indirect contact sensing, but very limited. So you need to make sure that the scene more or less aligns with what you have in simulation.
I see. And let's say we hypothetically wanted to expand that to vision-based RL or vision-based policy.
Yeah.
Do you think that just having maybe a good key point detector would do the trick, or maybe
Yeah,
not?
I think it depends on what you want. I think for cases like this, like which are still fairly structured, I think yes, you can get away with key point detections. I mean, you could also use motion capture in the real world, but defeats the purpose. But ideally, yes, you can do some key point detection in the easiest case. From very complex cases, I think you need to learn from pixels or from depth. I'll have like a future work slide on that. Yeah, there are a lot of limitations for current simulations, but we're trying to address those.
Okay, thank you. Super interesting.
Yeah, thank you for the question.
Yeah, quick question.
Yeah, go ahead.
And this is mostly around, I mean, so how many G1s did you end up going through for that research? Or did you have to like repair the knees or anything very often?
Yeah, so that's a good question. No, they didn't break as often for this project. That's a kind of impressive. Like the tracking policy is basically following Beyond Mimic, if you know the paper from UC Berkeley, and it's incredibly robust. Okay, like it's like if something works in sim, usually you'll see it working in real. So we didn't break robots because usually we do the first trials on a gantry and we have a lot of mats around. For this thing here, it's kind of crazy. Like uh, we tried it only 5 times, okay, because we don't want to break the robot, but it worked all the 5 times. So to give you an idea of the robustness, it's just incredible. Then of course there were issues with the hardware, but it was not about the robustness. It was more about the limitations, like the IMU backhand of the G1 would clip angular velocity at 10 radians per second because they didn't expect people to go beyond that. So we had to ask Unitree for a replacement to ship another firmware version basically to get us the IMU not to saturate at 10 radians per second to achieve this motion. Basically, we could do the motion, but we couldn't land properly because the estimator was failing. So that's the kind of hardware failure we see. Of course, robots break. I think like the G1, in my experience, is if you use it every day, then in 1 year you probably need to change it. You can always fix it with spare parts, but it suffers from wear. It's like at some point something is gonna break. The ankle, as usual, is the most critical part, but that's usually repairable. But if you break the waist, then probably just you have to change the robot or send it for repair at least.
Okay, thank you.
Hi, I also have a question. Sorry.
Yeah.
Sorry, I have a question about how to use the data. So currently, I know that even if you want the humanoid to complete some tasks in the simulation, most of the work still need to embed the reference motion trajectories as data collected in the reward to make the humanoid to imitate. But this limits the skill sets of the humanoids as they cannot deviate too much from such reference motions or explore better. So how do you see ways to improve the generalization?
Yeah, this is a really good question. The the issue I think is, people could naively think, I would say, like you could just add a task reward or like an exploration bonuses or something like that, right? And then somehow decay the motion tracking rewards at some point. That usually doesn't work. Just very, very hard. First, it's very, very hard to scale the different reward terms. And second, like it's not just the reward. I think one of the most important parts in the motion tracking is the termination. Usually trajectories are terminated when you deviate from your reference trajectory. So it's a really hard penalty because basically if you go away like 2 centimeters from the original trajectories, then the agent doesn't accumulate any more reward. So I think there are workarounds though going on in the future. You could imagine like this, you could distill basically, all these motion tracking policies into a single policy, and then you could keep improving the policy, for example, with real world fine tuning. That's, I think, a very promising direction. Other people think like, oh, you could use motion tracking data, for VLAs, and if you get VLAs to properly explore the environment, that's another possibility. So I think there are different possibilities there, but I think for the way we do things now, it would require an additional step. I don't see it promising to just add another term to the optimization.
Okay, yeah, thank you.
So what is missing? We touched on some of these points. So to really unlock, broad local manipulation capabilities, we need policies that can perceive the environment. If we look at the state of the art of perceptive policies here from Skilled, great locomotion can be achieved just by using depth maps or LiDAR measurements. But the issue is that, well, first, it is very challenging, as we were saying, to design all these complex environments in simulation. But more importantly, that doesn't really capture semantic information. Well, for locomotion, this means, you can't cross, a pedestrian crossing with just depth. But for manipulation, you're really missing out on a lot of more of semantic information, which is given by the actual appearance of the objects that we want to manipulate. So in regard to this, earlier this week, actually 2 days ago, we released a framework called Ghost Gym that allows to place your robot in a very realistic simulation environment and render egocentric images very, very fast at hundreds of thousands of frames per second on parallel environments placed on a single consumer GPU. The principle is to reconstruct Gaussian plots from online datasets, from scans with just a smartphone, or even generative models, video models like Google Veo. You will see one scene in a second. And basically can also reconstruct accurate meshes from the point clouds. Now, we open source more than 4,000 different scenes together with the framework. And the cool thing is that now you can directly train policies from pixels and transfer them to the real world without any articulated distillation procedure like teacher-student architecture for people who encountered them in the past. So in the paper, you see some sim-to-real experiments with a quadruped robot, also working on the humanoid side still now, and also some interesting semantic navigation that is enabled by training with RGB pixels. And this is, by the way, a scene generated with a video model, which is kind of crazy. So pixels are great. If you look even broader, we miss perceptive multisensory policies as well. We've done some work in the past on fine-tuning VLAs with both tactile sensing and sound. There is so much more that can be done in the setting of humanoid robots, which of course will have a lot of different onboard sensors. And finally, when talking about facility, I also mentioned RL fine-tuning directly in the real world, and there have been different works that might bootstrap this direction. For example, you could use demonstrations to learn a reward predictor and use it in the real world for online RL. Or you could use exploration bonuses to make sure that you target real-world exploration to specific regions of the state space to make this learning phase quicker and ideally also safer. And now these methods have mostly been showcased on simple robotic systems, and there are many open questions on how to safely apply them to the control of high-dimensional robots, such as humanoids. To conclude, I want to give you a takeaway and show you a little concept of how I believe things might turn out in the long term for humanoids compared to other learning pipelines out there. So if you look at LLMs, the paradigm that is emerging very recently is that you can train a base model in a self-supervised manner, maybe improve it with some supervised data, but then fine-tune it with reinforcement learning. And this paradigm is somewhat related to one that people in robotics often refer as large behavior models, where you often train a base model, but fully supervised with teleoperated trajectories, and then hopefully fine-tune it in the real world as needed. Now, my proposal for humanoids is slightly different instead, and targets learning really robust, low-level skills first, with reinforcement learning or through pure exploration, either in simulation or in the real world. Then you want to compose the skills, and if low-level skills have already been learned, there is a huge potential to do this with much less data, or even better with videos, and maybe ground all of this into language or something like a vision language action model. And finally, we can keep fine-tuning or reinforcement learning to refine for any other mismatches on real-world tasks. So with this, I'd like to thank you for attending this talk. As I mentioned before, I'll be joining UT Austin soon, so if you know of motivated PhD students, please reach out. Thanks again, and I'm happy to take other questions.
Nice. Super good presentation. Thanks, Carlo. So
Thank you.
yeah, anyone online or in the room have more questions?
I have a question.
Cool.
Thanks for the presentation. I have a question about the Ghost Gym. I know that it provides realistic rendering of the environments, but what's the point of having that for locomotion policies? Because for those robots, the depth image and elevation map from LiDAR is just enough to locomote. We don't need RGB, and it's very expensive if you want to process RGB images to understand the environment to do locomotion. Maybe for manipulation, that makes sense, but for locomotion, I don't really understand what's the point.
Yeah, so we did have an example in the paper actually, and it's useful for semantic navigation. Let's say you have a region in a room. We have this experiment in the paper where you're doing goal-based locomotion, and you have a region in the room that you cannot cross, and the region is just indicated by some painting on the ground. Okay, you don't see anything in depth. You don't see anything with lidars, but you can still give a penalty in the reward, and the only way you can observe that is if you have RGB pixels. And what we can see is that the depth policy keeps going, crossing that region, while the RGB policy can avoid it successfully. So similar to the example of pedestrian crossings, right? What if you want a robot to go through pedestrian crossings? Like they won't appear in depth or lidar, but they will appear in RGB. So there are a bunch of all these semantic reasoning examples that also make sense for locomotion, but definitely agree with you. With manipulation, it's just completely different thing. Like it is crucial. And I think that, one thing, like for example, Ghost Gym, it's all about static scenes for now, except the robot. I think for manipulation, we need to understand how to bring dynamic objects in as well.
Okay, and then a follow-up question. I know that you've used the Grand Tour dataset to provide realistic renderings, but are those limited to whatever Grand Tour provides, or you can extrapolate and have new environments based on what Grand Tour provides?
Yeah, so no, we actually have Grand Tour for sure. We have like a lot of scenes from Grand Tour, but we went around with, in the lab, for example, we would take a scan and in 2 hours it would be in our simulation environment. Or we used video. This scene here is a video generated by Google Veo, like with a prompt just written by us. And then we just take that video and we of course extract poses, extract the point clouds and the Gaussians and so on. But it's just a video generated by a neural network, which is also pretty impressive. So yeah, it's very diverse as an architecture.
Great. Thank you so much.
Thank you.
I guess I've got a quick question about your last slide on future work. And I guess it's basically, do you see any issues with being able to have good coverage of all of like the, what do you call it, sub skills? Yeah, learning skills beforehand. Like, do you think that's like solvable?
Yeah, that's a good question. The question is, how do you learn those skills, right? I mentioned here pure exploration. I think that's also a very interesting direction. I think one big problem right now is that we do mostly exploration through either vision or just states of the robot. which is, I think, not the same way we do it for humans when you talk about manipulation, especially. So humans explore through touch. That's pretty clear. Babies just want to touch things. How do we get robots to do this? I think that's a big question. And if we do that, I think we're going to learn a lot of primitive skills like pushing, stacking, rotating things, and this should emerge just simply from exploration. And then, of course, it depends. You could have like a robot watch a lot of videos as well and extract skills from that. So I think that's probably another scalable way. But I agree, like I think we can't, necessarily cover all of them. So that's why we need RL fine-tuning. We need like an interface for robots to, learn even more from instructions and keep adapting in the real world.
Okay, so the fine tuning here will also add skills, not just the fine tuning for the composing skills together.
That's correct. I think in the end here, you won't have like a skill-based policy. It will just be like a distilled policy. And ideally that policy can keep exploring in the real world.
Okay. So this has some similarities to doing hierarchical RL and combining some things together. Okay. I guess there's a lot more details here that I'm curious about because there's definitely some technical challenges in this plan.
Absolutely. And there are many, many different ways, I think, to implement it as well.
Okay. Yeah. All right. Sure. Thanks.
Yeah.
Okay, I think that will be it. Carlo, again, thanks again for coming. It was very great to hear from your research. Please keep in touch and best of luck
Thank
in
you
your
so
new
much.
position, all right?
Thank you for inviting me again. Bye.
All right, our pleasure. Take care. Ciao, ciao.
Take
Bye.
care.